So what I'd like to do today is I'll be spending just a few moments to share with you how we've used some Clarity node data in Bishkek, Kyrgyzstan. Before I do that, just by way of a perspective of where I'm coming from with regard to this topic. So I'm at Washington University in St. Louis, an engineer by training, focused exclusively on environmental type work on air quality. And at this moment in time, my team, which includes 5 doctoral students, I'd say just more than half of our work is focused on air quality monitoring using these types of distributed sensor networks. We have networks in the US, such as here in St. Louis, where we have partnered with a community that works with churches, because faith-based institutions in St. Louis are a very powerful way to get to the community at large. And this project has a strong environmental justice focus. So we have monitoring at 14 different churches outdoors in EJ communities. To the other extreme being the kindergarten network in Mongolia, and also through our work with Mongolia, helping them understand that what they might have perceived as being far from ideal aspects of these type of sensors, that you can actually do an incredible amount of useful work with these sensors, even if they don't perfectly agree with reference monitors. And that was a hard barrier. It took us a few years to break through that barrier and not just have people criticizing the sensors and saying that they weren't accurate. There's ways you can make them more accurate, but also even just using the raw data, there's a lot you can actually do. So again, before I start, just a real quick shout out again for this model of bringing people together. Also a shout out to Colleen and OpenAQ. Our group has been an early adopter in using the data that we would extract from OpenAQ. It was probably even 8 years ago or so that we were pulling data from OpenAQ for our work in Mongolia. And it has been an invaluable resource to us in our work. So what I'll focus on today is just a very brief story of our work with Clarity Node S sensors conducted in Bishkek, Kyrgyzstan. That's the capital of Kyrgyzstan. And just anecdotally, tomorrow I fly to Uzbekistan for a week of work, and then I'll go spend another week in Kyrgyzstan after that. So I want to acknowledge Rufus Edwards from the University of California, Irvine. This is a project focused on air quality and health, and Rufus is a health scientist and public health expert. And this work was funded by UNICEF. I won't read through all the names, but I just want to acknowledge that when we work on these types of projects, it's highly collaborative. We had our project team, but then we also had, with the outdoor air quality data, the network was funded by the Asian Development Bank, and it was not funded, the network was not funded for our project. It was funded independently. The Asian Development Bank provided the funding to the Kyrgyz Hydromet, essentially their environmental monitoring agency, and every step of the way, Clarity was involved. So really this trio of partners for the outdoor air quality monitoring was really, really crucial. And that monitoring network continues to exist. If you're interested in details about the overall scope of our project, we did publish a report precisely 1 year ago. This is showing the cover page, and our report is actually linked not only on the UNICEF website, but also on the Clarity website. There's a link to this report. So first, I just wanted to briefly share with you the overall scope of the project and how the distributed air quality network fit into the overall scope of the project. First, we did what's called a rapid situational assessment. And that's really out of scope from today's discussion. But the point was, Rufus and I went and met with more than 20 key stakeholders in the government, NGOs, donor organizations, to really understand their thoughts about the air quality problem and who the decision makers were and how decisions were made. And it was crucial to have these meetings individually, because the responses you get when you get all the stakeholders in a room is often very different than when you're talking to them one-on-one. And so that was really focused on the policy aspect of how do we prepare UNICEF for their entry points into being a stakeholder in the air quality and maternal and child health space in Kyrgyzstan. We took the outdoor network, the Clarity Node S network, again, funded by the Asian Development Bank, operated by the Kyrgyz government. And we used that to understand across the city, what's the spatial distribution of outdoor air pollution. We did our own measurements of indoor-outdoor air quality to come up with adjustment factors, since people spend most of their time indoors, to better represent exposures. We did an exposure estimation, and based on that indoor-outdoor air quality and time activity data, how do people spend their time indoors, outdoors, commute, at home, and so on. I highlight here in orange or yellow the key aspects in which the network data factored in. We did a survey of over 1,000 households to understand household demographics and their residential characteristics. What were they using for their heating sources and such? Did a health impact and economic burdens assessment. That is, we quantified the health impact, both in terms of disability adjusted life years, deaths, and also economic impact of those aspects of the health burden. And then really separate from this, in a follow-up household survey, we did what's called a contingent evaluation study to understand, well, how much would people be willing to pay for better air quality, and more importantly, for improved health. So I just wanted to share with you the breadth of this project, because you'll find all of this in our report, but I'm only going to focus really on how we used the distributed network data. That's all I'll focus on. So when we went into this project, we knew we needed to assess outdoor air quality in the urban area. And like all of you, one of our challenges is to really have a very concise statement of our goal or our objective. And in this project, what we wanted to do was quantify spatial variability in indoor and outdoor PM 2.5 to estimate annual average exposures. We were not interested in day-to-day variations. We were interested in the annual average, because most of the dose-response relationships for health effects are based on chronic effects or long-term averages. Our initial plan was to use data from 1 or 2 reference monitors, the US Embassy and the Kyrgyz Hydromet. Both have PM 2.5 monitors. Then to use 5 low-cost sensors as indoor-outdoor pairs, and we would move them from residence to residence for 10 weeks. So after a week of work, so what we would then get is some spatial information at 50 sites, right? 1 week only though, and both indoor and outdoor when we did that. And the idea would be to tie it back to those reference monitors. So if 1 week the reference monitors are different from the next week, that would tell us how to adjust our low-cost devices based on where we were in the city to essentially come up with a wintertime average spatial map based on 50 data points, but tethered together by using the reference monitors to tether together the time changes. This would work. It's been done, but it's very far from ideal. And you're going to introduce a lot of what they call in the health community measurement error. And that's different from the error we think about as sensor people, which is how accurate and precise is my sensor. In the health community, measurement error means how well am I estimating exposures? And this approach would have been quite crude, to be honest, in that sense. Well, we were really fortunate because, as I mentioned, in parallel to our work, ADB did fund the Kyrgyz Hydromet to deploy a 50-site Node S network across the city. This was amazing. So we were able to utilize or exploit this network, which raised our analysis to a whole nother level of accuracy and precision. And a shout out here to Levi and Sean, who facilitated getting the approvals from the Asian Development Bank and the Kyrgyz Hydromet for us to have access to the data, because that's not always taken for granted or trivial. So again, really critical of the role that Clarity played in facilitating us getting this data. Now, just one slide is a digression. I respect that most of you already have your networks up and running. I did want to share with you something about strategies for the design of projects. So we're going to focus today on what can you do with the data from a distributed network. But I wanted to share with you one slide on the design of networks, because we spend a lot of time in my group doing design of networks. And this is for air quality, like low-cost sensors. This is for temperature networks in urban areas, for noise networks in urban areas. We have noise networks right now, temperature networks now that are out there. So here's an example where we're getting ready to deploy this summer in Louisville, Kentucky, a network of 60 VOC samplers, essentially sponges that we bring back to the lab and analyze for more than 100 volatile organic compounds. So the question will come up, how do we decide where to put these sensors? Well, in this case, our hypothesis is that unlike PM 2.5 in Louisville, which does not have much spatial variation, there really aren't hotspots. For VOCs, we anticipate hotspots. So what we do is there's actually an algorithm you can run, and we do this work in GIS. It's called the location allocation analysis, where we take into consideration roadways and population and restaurants and green spaces even, and additional factors. And what we do is in this modeling, we ask the question, given 60 sensors in this case, we could have asked the question, given 40 sensors, but given 60 sensors in this case, where should we put them to best fill in the space of capturing the variation in roadways, capturing the variation in population, the variation in restaurant densities, the variation in green space. So the idea is designing a network where you can't put one everywhere. So you ask, how can I best capture the variation in the factors that I think might be contributing to air pollution? And it came up with the 60 sites shown by the stars, and that's where we're putting our network. So again, in the case of the Bishkek project, the network was already up and running. It turns out it's with only a few exceptions that we did identify, there are hotspots, including what we think is a commercial sauna, actually. There really aren't many hotspots that we identified when we're looking at the urban scale, and this network, as it was implemented, really served our purpose, which was wonderful. And this network design might not have actually brought us much added value. But if you're ever interested in network design, please reach out to me. We're always interested in chatting about it. With regard to data analysis and what you can do with your data, you've got this great workshop series. You have the Clarity team with deep expertise. Also, don't hesitate to reach out to us if you're interested. We've given 2-day workshops in Mongolia on nothing but analyzing data, whether it's a few regulatory monitors or distributed networks. In that case, it was for the Mongolian government. All right, so data validation, always a big question. As you know, through the Clarity dashboard, there is a certain level of data validation that's done in comparison to reference monitors when that data is available. And that's very helpful. And in many cases, that's all you need. You always want to define what's your objective with your data validation. And recall, our objective was annual average exposures. So I didn't need to worry about how it compared to a reference monitor on an hourly level or even a daily level. I need to understand how it compared to a reference monitor on a seasonal average, for example, and look reference monitor level. I bring this up simply because sometimes we get pressed into really worrying about data adjustments to be reference monitor-like. And it really comes down to how important is it for your data to be representative at the hourly level, which it often is if you're reporting to the public in real time, as compared to other objectives, like mine, where we could actually do a much more efficient data validation and data adjustment process, right? So people wanted to take our validated data and use it for looking at the distribution of daily averages across the city. And we said, no, don't do it. That's not that's not how we developed our adjustments. There is a caveat, and you take a place like St. Louis, and if we co-located with a reference monitor and applied that adjustment to our network, I would feel really confident about it. In some other cities, like in Bishkek or Ulaanbaatar, I'm less confident about it because you have really large spatial variation in sources And those sources are leading to local air pollution that to which the sensors might respond differently because of composition or size distributions. We don't take that into consideration. It is a caveat with at least some locations. So here's the network. Clarity Node S on the right-hand side, with which you're all familiar. On the left side, we ended up, after our quality assurance process, keeping about 35 to 40 of the sensors in our analysis. The larger the bubble, the higher the annual average concentration. Now let's recall that in the US, we just lowered our annual standard to 9 microgram per cubic meter. And here we have sites in the city where the annual average is nearly 10 times that number for the annual average. All right, so some really extreme air pollution. And what you can see immediately from this figure that's really compelling is the spatial distribution of where the high and low concentrations are. Right? The north side of the city is very polluted. The east and west sides are next. And the south side is relatively clean. I use the word relative. Now, there's a couple of key. So here we have a difference in annual average of 400% across the city. In St. Louis, that difference is about 10 to 15%, right? So huge differences. This network was invaluable. Now, a couple of points. The triangle is the US Embassy data. It's actually in the cleanest part of the city. That data is easy for the public to get to, but it's not representative of most exposures in the city. The square is the government data, which is not regularly publicly available, although it does well represent the average across the city. So again, it shows the power of this network. Another key point is the red box, because going into the project, it was believed that transportation was the most significant contributor to the PM 2.5 problem. That red box is downtown, which is the most congested part of the city. And it is certainly not the most polluted part of the city. So this was really important to shift the conversation away from a focus on the central power plant, which is located in the city, and transportation, and to respect that there's other sources that are not just important, but they're dominant for the air quality problem. Well, what is dominating? Here's what you can do with data. So taking this sensor data and using geographic information system software, we were able to create this heat map or surface, which we feel has a high degree of accuracy, honestly. There might be a few hotspots that we're aware of, but by and large, this heat map represents the concentration across the city on the annual average. And we can use this heat map now and GIS tools to pull out an estimate of the air pollution at any unmonitored location. Now, what's causing the air quality problem? What's the dominant source? From our household survey, we get the data shown by the gray vertical bars, which is the fraction of homes in a neighborhood that are actually burning coal in the wintertime to heat their home. So what happens is in the neighborhoods, there are these coal piles, and they bag up the coal, and you take your car and you pick up a bag of coal and you burn it in a stove. There's an example of one type of stove. And what we see is the higher the bar, the higher of homes in that neighborhood that are heating their home with coal in the wintertime. And you can see a direct relationship where the highest polluted areas are where people are doing residential heating with coal, and the cleaner areas is where people are not heating with coal. Those are houses that are perhaps on the natural gas distribution. There's also a lot of apartments rather than single homes in that area. You'll note an anomaly here of high pollution but low coal burning. I won't describe why that is today, but there's actually a reason, and it's that these coal burning estimates are actually not fully representative of the neighborhood coal burning, because for our survey data, we were looking at something else about economics of households, and those are very small apartment complexes surrounded by homes burning coal. But these were very small apartment complexes in our survey data set. I don't want to dwell on this graph, but it just shows different ways we can think about representing the data. On the left side, we see on the x-axis the annual average PM 2.5. And on the y-axis is the fraction of the population that is experiencing a certain level of air pollution. And the point here being that because we had this beautiful distributed network and we created a heat map, we overlaid this with a one kilometer square resolution population map. And we could estimate exposures across the city for the whole population, not just people living near monitors. And that's what these curves represent. So whether we receive the population data from our household survey or from this 1 kilometer resolution census data from 2019, you see sort of the same pattern. You've got about 50% of your population exposed to 30 to 40 microgram per cubic meter. You've got about 10% exposed to 20 to 25 microgram. But unfortunately, we've got 90% of our population in the city that annual average exposed to more than 50 microgram per cubic meter. And the bar chart at the right is just a way of showing that the same information, but in the context of World Health Organization guidelines, where we have a significant part of our, more than half of our population doesn't even meet the most lax interim guideline for the World Health Organization. Now, another thing we can do with this data that's really exciting is looking at time of day patterns. They vary dramatically across the city, and it gives us more insights into why we see the patterns we see. So what we see in the black is the US Embassy site, where it doesn't have a morning rush hour peak at all, and actually it has an early evening peak. This is actually because the south side of the city is the foothills of the mountains, and we have airflow patterns that go up and down from the mountainside that affect airflow across the entire city. And what happens is in the late afternoon, the wind direction shifts 180 degrees and brings the pollution from the city down to those monitors in the foothills, although it's very diluted at this point. Whereas during the daytime, everything's just being pushed from the bottom, from the south up to the north. The green is downtown. Here's the morning rush hour peak in the green right here. The red and the blue are in these residential areas where people are burning coal. And notice that the morning peak shifts to earlier hours. This is indicative that it's not traffic making those peaks, but it's people waking up in the morning and putting more coal in their stove when they wake up in the morning after having it after having it partially burn out overnight. So even little things like the shift in where the peaks occur can tell us something about behaviors. And then just notice how high these evening values are. This is wintertime average. Some of the neighborhoods nearly 250 microgram per cubic meter at night on winter averaging. So again, this data is so powerful to here interrogate how meteorology is affecting air quality across the city. And while we had 50 sites, and again, we looked at 35 to 40 of them, all of them had the same pattern in the early afternoon where all the concentrations collapsed to about the same value, on average 50 microgram per cubic meter. The whole city looked the same for a few hours every day. And that again was this profound meteorological effect because of the airflow and how it coupled with air moving up and down off the mountainside and would affect circulation patterns over the entire city. So to wrap up, and I'm highlighting in red areas where being able to use the distributed clarity Node S network data was pivotal to our work. So a moderately dense network here on the order of one sensor every 5 square kilometers. We were able to identify this incredibly high spatial variability across the city. We were able to do exposure estimation at 1 kilometer resolution and able to identify this profound influence of the mountain valley airflow effect. When we coupled this data with our household survey data, the indoor-outdoor data, it highlighted that residential coal stoves are the dominant source of air pollution. And indeed, the indoor measurements were closely coupled in time to outdoor concentrations. The indoor stoves had chimneys. What they were doing was not causing directly an indoor problem, but rather what they were doing was contributing to the neighborhood scale outdoor problem that then infiltrated back indoors. So, and then this all was the foundation for the health impacts analysis. So my last slide, what are the implications? So what happens? Well, While many emission sources are important, this together with some modeling done by a Scandinavian group for the United Nations Development Program really shined a bright light on residential heating in the wintertime with solid fuels like coal. And what we really need to do is transition away from this. That said, okay, so we need interventions to reduce PM 2.5 emissions at the neighborhood or larger scale. If I've got a coal stove and I replace it with a different type of stove that's not coal, is not a solid fuel, my indoor air quality might not improve at all in Bishkek. All my neighbors have to switch over too, because it's a neighborhood scale outdoor effect that infiltrates in. In the absence of these emission reductions, which will take time, we can still reduce exposures using things like air purifiers, and that's part of the reason I'm going back to Bishkek on this trip that starts tomorrow, is a program where we're trying to get funding to provide air purifiers to homes with pregnant mothers and small infants. And it's a loaner program of air purifiers. They have to give it back after their infant's 1 year old, and we'll loan it to someone else. The World Bank announced in November of last year a $50 million interest-free loan to the Kyrgyz government for air quality. And our work here provided a weight of evidence for how to prioritize, or the need to prioritize, residential heating in this context. In the draft action plan, residential heating was not mentioned. In the final action plan that the World Bank approved, it's one of the three main elements of the program, is the transition away from solid fuels for heating. And then the continued operation of this Clarity Network is going to be very useful to assess the air quality impact of the interventions. It includes improving stoves. It includes a massive program on transportation, to cleaner vehicles, on urban greening. And the key is, with this network, we can really assess with high spatial resolution what impact these particular interventions are having. So I'll stop there, and thanks so much for the opportunity to chat with you.